Hey guys, my name is Salman Chisti. I go to Langley Grammar School. My candidate number is 3174, my center number is 51411. I've made a realistic gravity simulation for my computing project. It's designed to be used in the classroom, or the teacher can set homework and the students can take it home on a USB or download it from the school website. Okay, so on the introduction screen, what you have is an explanation of what gravity assist is. I will not explain that because it would just take too much time, but basically you use another planet as a slingshot to travel further. So you go to your tutorial screen and you're greeted with like more in-depth detail of what gravity assist is and like how the program works. So it tells you where the results are saved and has a labeled input screen. You have your drag formula and you have controls. So you can go back to your home screen and we'll go straight onto the input screen. So over here, what you have is tooltips, which explain each individual box. Because if you don't know what to do, you just hover over these and it explains. So you input all your variables here, your rocket variables and your second planet variables. And you have an incremental slider, which is directly proportional is to the game speed, so it's a linear relationship. And then you have a tick box over here, which allows you to have extra features, which changes the speed of which the planet moves. You don't have to have that, but that's if you want to be more advanced. Okay, so for validation, I've used regular expressions so that people can't enter text like characters, like letters, into a integer value and stuff like that. So I use regular expressions. So over here I cannot type letters or special characters. That's not my keyboard not working, as you can see it's in the bottom right. I can type digits in each of these. However, the special characters do not work here. Drag coefficient, on the other hand, needs a decimal place. So I allow you to have one decimal place. You can't have more than one, because why would you ever need that? Same for cross-sectional area, because it's such a small number. Therefore, you can have a decimal place. Then you have your planet mass, because it's an exponential form. You can have a decimal place. You can't have letters for any of these boxes, basically. Okay. And then when it comes to coordinates, I allow you to have one negative per text box and decimal place. Why am I using 6 like the whole time? Okay. Same for these coordinates as well. Okay. So to save time, I'm just going to fill this in with defaults. And if the teacher wants everyone to use the same values, they can just use the defaults. Okay. So if I remove one of these and I launch, it will tell me to fill in all the text boxes. And if I want to save these variables for later, for example, like this, and drag coefficient of 1.6, even though that just might be ridiculous for this scenario, I can save these for later. So test launch. I can save this, load my defaults, or I can go back, and then go back in. I can load my test launch. It's not case sensitive, so it's all fine. That's my test launch variables, the 1.6. All these variables. Can load other files, so someone can put their files into this PC or a USB and they can load it in. Say my friend Marcus might have made some. Can load the variables in. I haven't made my own variables, so if I try to read, it'll give me an error and it'll say invalid file name, please try again. It will highlight the text and I can type straight away back. Okay, so I'm gonna just go by the default variables. We're gonna choose an X position of 950. We're gonna save this as far run 1. Okay, we're gonna increase the game speed a bit. We're gonna launch the program. As you can see, the X, Y, and Z position is changing, updating. Everything updates with the game. The distance from the center of the Earth, distance from the second planet, and the total displacement is all accurate. The acceleration towards Earth is inversely proportional to the distance squared. And you have your acceleration towards your second planet increases as you get closer. So you can see we're like tilting because we are moving towards the planet at the same time. We're not moving that much, that's why we're still moving up a lot as well. And look, notice the variables. The planet's moving a bit. We haven't tweaked it. And notice the coordinates. And as you can see, we're slingshotting sort of, not that much, but we are. Okay. So notice these. I'm going to exit right now with escape. And I'm going to go to my C drive. And I will to my output folder, results. And you did not crash. 560.95. That was the same as when we exited the program. Yeah, it tells you if you crashed or not, and it gives you all the variables which were displayed on the screen. So that's really helpful if you want to tabulate this information, if you're in a class and you want to compare results and then draw your own graphs and such. Okay, so we had a planet position of 950, 500, 0. So in this scenario, we did not crash. So what we're going to try to do, we're going to make it crash. So there's two ways we can go about this. We can make the acceleration towards the planet be so great that we just travel all that distance and crash into it because we increase the mass of the planet. Or we could move the planet towards us and keep the same mass. How the acceleration will be higher because we're closer. I'm going to choose to do the latter. We'll load our variables from before actually. Sorry, why am I typing it there? We'll load them from before. So we only change that variable. I will change this to 300. So therefore we're going to have a high acceleration into the planet and probably crash. We're just going to launch like that. And we'll see what happens. So as you can see, we're only like about 580 kilometers away. The acceleration towards the planet is so high. It's basically the same as our thrust. As it's higher than our thrust, we're probably going to crash because our acceleration is lower than acceleration to the other planet. We're probably going to crash into the planet because it's high acceleration into it. And look how high it's getting now. So that basically means to stop us from. So okay, there you go. We've crashed. We'll go to our results, and your rocket crashed into the planet. Oh no! Gives you all your information, your XYZ position of the rocket and the planet. So when it crashed, here's the info. So we've basically matched the position of the second planet because we've crashed. Okay. So we're gonna keep that up there. And how are we going to successfully have a gravity assist slingshot without crashing into the planet? I didn't actually save the variables, so I remember from before it's 300. So in order for us to not crash, what we have to do is we have to increase our thrust. Because as you can see, our acceleration before wasn't high enough to bypass the planet. So we've increased our thrust a lot, and position's fine. And we're just going to save this as 1. Sorry, it's down here. 1, 3. We'll save it in case we don't actually bypass and we do crash again, so we can tweak it later. So we'll launch. Hopefully we don't need to do that. You learn from your experiences with this program. You learn how each variables interact. And as you can see, we're moving way faster. That's because our thrust is higher. Our game speed hasn't changed. And look, our acceleration is higher than the acceleration towards the second planet with the thrust. Therefore, we were able to bypass. And we used it as a slingshot. So there you go. You did not crash. Congratulations. Your XYZ positions and or your acceleration. So there you go. I hope you've learned something as well from watching this video about gravity assist. That's my aim for this program, to teach people about gravity assist. I didn't actually take physics, so I had to teach myself this. It was very interesting. So this has been Salman Chisti from Langley Grammar School, candidate number 3174, center number 51411. I hope you guys enjoyed, and I will see you next time. Well, maybe not next time. Okay, bye.